I wanted to explain kind of where my research at Topos came from. So the history and current state and direction of this branch of Topos, the connected intelligence branch, and in particular, why polynomial functors. So I was in pure math and graduated from Berkeley in 2007. And I moved from pure math to applied math back then after reading this book called The Moment of Complexity, Our Emerging Network Culture. So in this book, it was saying how networked culture with the internet and all that sort of stuff is going to make life, as the speed of communication increases, life is going to become increasingly complex. So he said that we won't know what's true. And so I was kind of anticipating fake news since around 2007 with the idea that we just won't know what's true, and it'll be harder and harder for different communities to understand what's going on, that anomalies will become the norm. So we'll be seeing stranger and stranger things, and more will be different. And I had this thought that in order to steer effectively, if we want to tackle big problems, crises, et cetera, we're going to need better communication. And that communication is really at the heart of all of our problems. We don't understand each other well enough. So I wanted to help with this problem using math because I knew firsthand that category theory organizes the immense complexity within math. And I'd always loved math in connection with reality, like what it can actually do for us. So I figured that category theory could apply to information and communication, that those are structured systems. And so having this idea that mathematical languages are accounting systems, ways that you give accounts in a formal ways of talking about things, I wanted an accounting system that could help us steer even as the complexity continued to grow and grow. So what I was working on back then is trying to understand how we communicate even though we have different worldviews. My brain structure is very different from your brain structure, like more different, let's say, than our fingerprints or retinas or the veins in our, like the way our veins are going through our body. Our brains are very different. And yet, even though we're holding information in these different data storages, or whatever you think of a brain as, even though they're very different, we're still able to understand each other. So I wanted to understand what mathematically could be going on that allows different data structures to be able to exchange ideas. So to get started, I imagined just for the sake of getting started that we're just databases. So a database consists of two parts, a schema or worldview or ontology, which just means that it's what you conceptualize the world to be made of, like what the kind of schematic, high-level abstract way of seeing it is. And then you have a memory of all the examples that you have so far as they fit into that schema. So all the dogs you've seen and all the parents you've seen and all the amusement parks you've seen, every one of them would be an example of some kind of thing in your worldview. And the idea is that you and I have different worldviews, and yet we can migrate data, we can send our examples and talk about them, and my examples can make sense to you. And so I developed this theory of data migration to try to understand how different databases could communicate even though they had different worldviews. But in both a metaphorical way, like in both the history of my thinking on this subject and, well, we'll get into it in a second, in a meta way, as we interact, we change. So basically, as I was interacting with several companies and granting agencies and other people who were interested in the work, MIT was employing me. I had a grant from NASA and FOSR and Office of Naval Research, and I was getting interest from like consulting and stuff like that at Amgen and Johnson & Johnson and influencing stuff at European Spallation Source. I was working directly with these practitioners, but I noticed that my story was missing something. And namely, I would notice that the database story was just too static. So for example, Amgen and Johnson & Johnson needed to understand processes, not just data. I thought that I could maybe do everything with just data, but it just wasn't easy, it wasn't working well. So I started from scratch and developed what I call the operatic approach to compositionality, where you have operads, meaning you can put little things inside of things. And I thought, oh, maybe this will allow me to understand the kind of fractal nature of recipes or the fractal nature of processes, how you can just keep zooming in and in and in or out. And so I was thinking about dynamical systems and wiring diagrams and mode dependence. And the idea was you have these dynamical systems, which you could draw as these boxes. So Y1 would be a dynamical system, but inside of it would be the smaller dynamical systems, X11, X12, X13, Anyway, what a dynamical system is it's a way of, it has some internal state like I do right now, or like my brain cell does right now. And then that brain cell, that state is somehow exported outwards along some wires or some connections, and is found by or heard by some other dynamical system, some other cell or some other person. And when it goes into that other person, it changes their state. So you hear these words and maybe you change your state a little bit. And then your facial expression comes out and goes to some other dynamical system. So this is how I was thinking about dynamical systems being wired together in some bigger dynamical system, the ability to nest things. And I called these wiring diagrams. They're similar to string diagrams, except they're for what are called operads, so for nesting things. But I was working with people in the field. I was working with people at Honeywell and NASA, again, on the same project, and then working with people in the materials science department at MIT and the robotics department. And I noticed that working directly with these people, it turned out that my story was again missing something, which is that things go in and out of contact. So we weren't connected on Zoom before, and now there's a new connection between us. So bonds in materials break and form, and communication links are dropped. So I developed what I called mode-dependent wiring diagrams, where the who is connected to who could change based on what was flowing on the wires. So if I say goodbye, then maybe we separate or something like that. And the problem was that the math of this was really ugly. So even though it was published, I never really took it around to the applied category theory community because I didn't like how it looked enough. It wasn't elegant. But then it's in December 2019, I felt like I hit the jackpot because everything changed. So when I found polynomial functors, it was like finding Aladdin's lamp. I just felt like, wow, there's just unlimited abundance here. Poly, this category that I found that many other people have found before, remains the most articulate and highly structured category that I or anyone I've talked to has ever seen. So it was as though Poly invited me into this courtyard when I was searching for mode-dependent interaction. That's what I was there to find. But once I was there in that courtyard, I found a lot of my past work, like not only dynamical systems and wiring diagrams, all living very easily and nicely in Poly, but also databases and data migration were just living there. I wasn't looking for them. It was like I came into this other courtyard and some old friends were sitting there. And another garden has type theory, another garden has deep learning, another garden has cellular automaton, another garden has Shannon information theory. And as Andre Joyal said, it's like a treasure chest. So here's this amazing garden, and we had these luminaries from category theory, not applied, just pure, all there also. Well, not just pure, but also computer science and type theory and all sorts of stuff. So it was really, really amazing to see all that. So for me, what Topos does is one of the most essential things we do is we help make sense. So Topos makes sense in the sense that we're trying to produce the ability for people to understand the world. Herbert Simon got his Nobel Prize for this book called Administrative Behavior, but he went on about organizations, but he went on to be a pioneer of AI. And the connection is that at their metaphysical foundation, I think that organizations and organisms may have the same nature, namely that we're built out of these collectives of interacting parts that rearrange ourselves to creatively harmonize. In other words, some things feel bad, some things feel good, so we need to harmonize. But to get there, we need creativity and the ability to find new ways of harmonizing with our surroundings as they change. So I think every living thing, including and every organization, has to maintain a sense of its surroundings, how it lives, and its role, what it actually provides those surroundings so that it gets to be there. And so we're doing it here together right now. We're trying to build a sense of what we can do together that is worth doing and that kind of serves and is naturally and creatively a part of the world we live in. So I want to use Poly to understand how systems build the sense of themselves. I want to, rather than intervening on the world, it seems to me that we're already part of the world. There's no intervening on it. There's no changing it. We are the world interacting with itself. So our programs and our intelligences and everything we synthetically produce and have naturally are just part of nature. And so what I want is some sort of accounting system that enables like how you would account for how cells, humans, and organizations fit into and understand their role in the functioning of the world they inhabit. So that's it. Thanks.